So we'll start with the 2D from the separable differential equations. Was that the one that ended up with an inverse sign in it, I believe, in your final answer? Yeah, okay, so it went through and we got y equals, I believe it was the inverse sign of e to the x to the fourth minus 1. Does that look right? So that was the solution I got to it. I think that was not too crazy difficult to get, I hope. But then the issue a lot of people have been having with that one is finding the interval of validity or the domain of it. So the first thing we have to do is think about inverse sign. And so we should recognize that inverse sign has a domain itself of whatever's inside of it has to be between -1 and 1, because otherwise you can't take the inverse sign of anything that's not between -1 and 1, right? Because when you take the sign of something, you always get a value between -1 and 1. So if you're going the opposite direction, you got to plug in something between -1 and 1. So that tells us that e to the x to the fourth minus 1 has to be less than or equal to 1, greater than or equal to -1. And so from there, two things we can do is, one, we can think about e to the x to the fourth minus 1. And e to the x to the fourth minus 1 is always a positive number, because no matter what x to the fourth minus 1 is, if I do e to that power, I always get a positive number. So since e to the x to the fourth minus 1 is always positive, I can just ignore that part of it. And because that's always true. It's always greater than or equal to -1. So now to clear off the e, we need to take the natural log of everything. So the natural log of e to the x to the fourth minus 1 gives us x to the fourth minus 1, which is now less than or equal to the natural log of 1. And what's the natural log of 1? Should be 0, right? And so if we add the 1 over, we got x to the fourth is less than or equal to 1. And now, well, we square root the x to the fourth, giving us x squared. And it becomes a compound inequality again. X squared is less than or equal to 1, greater than or equal to -1. And once again, we can think about x squared. Well, x squared is always positive, right? So I can ignore that piece of it again, and we're once again just left with a single inequality. And if x squared is less than or equal to 1, that tells us that x is less than or equal to 1, greater than or equal to -1. So that would be the domain of it. There are no discontinuities within there. And so that would be the entire interval in which it's valid. Does that make sense for 2D? Okay, so for 2E, 2E is one that I wouldn't really expect you to have to do on the AP test. In general, for intervals of validity, they don't even ask them on the AP test. They used to about 10 years ago. But in the last 10 years, they've just kind of gone away from that, and they just want to know what the solution is without worrying about the interval of validity. But I still think it's important for us too. So specifically with this one, which you need a calculator to find, I'd be even less worried about seeing that on the test. So I think for 2E, what did it come out to be? It ended up as, was it y equals, I think the negative square root, x squared in there, plus tangent x plus 25. Or no. I'm going to go ahead and assume that's right, because I'm pretty sure that's what it was. So the restrictions of the domain of this, there's two different things we have to take into account. One, when is the thing inside of here greater than or equal to 0? Because that's a restriction on the domain, right? This x squared plus tangent x plus 25 has to be greater than or equal to 0. And also, tangent x gives us restrictions, right? That gives us restrictions for x equaling pi over 2 and 3 pi over 2 and 5 pi over 2, and also the negative versions of each of those, right? Because that's when tangent has asymptotes. And so cosine is 0. That's a 0 in the denominator, and it's a discontinuity. It's a vertical asymptote. Good or no? And so our initial condition was x equals 0, I believe. And so we know that we're going to be cut off by the first asymptote. So our value here is going to be pi over 2 is going to be our first asymptote. That's going to be our ending point of this interval. But we've got to figure out the starting value of it. So we got to figure out when less than 0 does x squared plus tangent x plus 25 equal 0. So you could do that with your graphing calculator by just graphing x squared plus tangent x plus 25. And I would do that on my graphing calculator, except that mine doesn't work properly anymore. So I would just put it in here. And if we look, I'll probably zoom out a bit here. We've got a value of negative 1.534. And that's going to include our x equals 0 value here. And then we're going to hit this asymptote of pi over 2 before we come back down and hit this value. This is more than pi over 2. So we're going to go from negative 1.534 to the vertical asymptote at x equals pi over 2, which we can see, lies to the left of this piece and to the right of this piece. Does that make sense? Oh, I didn't do that.
It does make sense.
Negative 1.534. So from the graph. And I may have written that pi over 2 value as a decimal on my on my answer key. I'm not sure if I did or not, but everybody good with 2D and 2E? Then I got a whole laundry list of other questions people have thrown in here while I've been working. So next one will be 1A. How did I get rid of the constant using K equals E to the C? So good question. I don't remember what that question was. What did the question start out as for 1A? Anybody?
dy over dx is equal to xy over x squared plus 1.
Xy over x squared plus 1. And this was, sorry, is that right?
That's right.
Okay. And was there an initial condition here or no?
No.
Okay. All right. So we have dy over y equals x dx over x squared plus 1. Natural log absolute value y for this one. And then how did you integrate x over x squared plus 1? What did you need to do with that? You need to let u equal x squared plus 1 so that d was 2x dx. So we'll put in a 2 and a 1/2, giving us 1/2 the integral of du over u. Good or no?
Good.
Okay. So now we're sitting here looking at natural log absolute value y. This is 1/2 natural log absolute value of u plus our constant. We can get rid of the absolute value because x squared plus 1 is always positive, and we can throw the 1/2 inside of here if we want. as a power. So x squared plus 1 to the power of 1/2 would just be square root of x squared plus 1. And so then I would exponentiate that. And that gives me absolute value y equals e to the ln root x squared plus 1 plus c. And so I assume this is where the question comes in, is how do I get rid of that plus c there? Well, what I did was, to start with, I said, let me get the page here. I first said y equals plus or minus square root of x squared plus 1. Yeah. Times e to the c. And that's exponent rules. E to the a plus b is e to the a times e to the b. So times e to the c. And then normally we don't like to write these things e to the c as like a constant like this. We'll just call it some other constant. So we're just going to say let e to the c equal k, some number, because that's all it is. And then we just write like this. But other than that, I mean, you could leave it as e to the c, and there's no problem with leaving it as e to the c. But standard convention is if you have some sort of weird exponential constant that you just say, all right, let's let that equal some other constant and call it good like that. Does that answer your question? I went through the whole problem when you were just asking about the constant, but yeah, okay, cool. All right. Any other questions on any of the homework assignments before I move on to the questions from the limit multiple choice stuff? That's all I've got at the moment. Does the sign of the constant matter? Would subtracting the constant just mean another constant? Yeah, I mean, the sign of it doesn't really matter. The only time you have to worry about doing operations with the constants is when you're solving for your constant, which is why when I told you guys to do the separable differential equations, like solve for the constant immediately after you integrate. That way it's always just a plus c, and then it's a number in there that you'll deal with afterwards as you solve for y. So yeah, c is 2c, is 7c, is negative 8c. They're all the same. They're all just a constant. And so as you're working through and like manipulating that constant in different ways, like we did with this one, it can just become some other constant at the end. Technically, what you should do if you end up with something like negative 3c, minus 3c at the end, if you want to just write it as plus c, you should have called it like minus 3c sub 1 the whole time, and then at the end say plus c, and write off to the side negative 3c sub 1 equals c, and then call it good from there. Does that make sense? Does that answer your question? Okay. Carrie, you good on that slide now or no? Or should I stay there for a bit?
Yeah, I'm good.
Okay. Any other questions on any of the differential equation homework stuff? If I ended up something like square root of c or the natural log of c, same deal. I mean, you can write it as square root of c or ln of c, or you can just, like I said, like I was sort of saying before, I would write it like as if I went through and I ended up with y equals whatever plus the square root of c. I'd just call it the square root of c1, and then at the end just say the same thing plus c with square root c1 equal to c. Same with natural log, same with any other thing with it. And you don't even have to do that. You could leave it like this, and if you don't define it as such, like I'm not picky about that, and the AP test isn't going to really care most likely on that either. It's just good habit to be in of making sure that you've defined things properly all the way through. It doesn't really matter much in our class or even Calc 2 or Calc 3 so much. Calc 3 a little bit. But when you finish Calc 3 and move on to a specific class on differential equations, how you define your constants really starts to matter. But at this point, it's not a big deal. Anybody else on the homework questions? All right. So first question somebody just asked me about a second ago was number 20 from the multiple choice. What was number 20 from the multiple choice? I was trying to flip to it in the book I stole those from, but I'm in the wrong chapter. Is that, I didn't get it down last period. Is that the x sine 1 over x one? I think it was. Okay, so the limit as x approaches infinity of x times sine of 1 over x. So initially what we would try to do, right, with any limit is we just plug in the value, and you know, it's infinity, so weird things happen with infinity. We end up here with infinity times the sine of 1 over infinity, and the sine of the 1 over infinity is 0, and the sine of 0 is 0. So we end up with infinity times 0, which usually is only an indeterminate form that they talk about in BC, so I'm a little surprised that this book put this one in here. But 0 times infinity is indeterminate, just like infinity over infinity is, just like 0 over 0 is. The reason being, well, you know, you multiply something by infinity, you're supposed to get something infinite. But if you multiply something by 0, you're supposed to get something that's 0. Well, I can't both get something that's infinite and get something that's 0. So this is not always the same. And as we think about it, we're thinking, you know, we're approaching infinity and we're approaching 0 for these, right? Sort of depends on how quickly we're approaching infinity and how quickly we're approaching 0 for each piece of it. And so what we need to do then is find a way to convert it into something that is no longer 0 times infinity. And the best way to do that for this one is to do a u substitution. So we've dealt with a bunch of functions that were like sine of x or sine of 5x or something, right? Sine of u, but not so many that were sine of 1 over x. So if we could turn that 1 over x into u, let's let u equal 1 over x, then that's going to allow us to rearrange and manipulate this a bit. So if u is 1 over x, I'm going to get a sine of u, but I'm still going to have an x here. And so that x will need to be rewritten in terms of u. So what does u equal if, I'm sorry, what does x equal if u is 1 over x?
1 over u.
1 over u, exactly. And as x goes to infinity, what should u be going towards?
0.
0, right? And so we should then be able to rewrite this as the limit as u approaches 0 of sine of u over u, right? Because x is 1 over u, so it puts a u in my denominator. U is 1 over x, so that just gives me a sine of u. And now this should be a limit that we have memorized, right? The limit as u approaches 0 of sine u over u should just be 1. And if by chance we might have forgotten that this limit is 1, you can always, if you want, apply L'Hopital's rule to this and get the limit as u approaches 0 of cosine u over 1 or cosine 0, which is 1. Does that make sense to everyone?
Yes.
I think I've gotten to all the ones that people asked for in the chat. Does anybody have anything else that they'd like to talk about? Any of these other ones? Probably from the first half of that multiple choice. I think it was 42, so the first 21 or so of them, first couple pages of it. Y'all remember how to do all of those perfectly, no issues? Everyone's feeling confident, or you haven't looked at them at all, so you don't have any questions? All right, if there's nothing else, we'll move on to what we're going to do today. So by Wednesday, I would really like it if you have finished all of the multiple choice in that limits section so that we can go over any questions 1 through 42 from the limits. And you probably saw that I put up a derivatives one this weekend sometime. I don't remember, sometime this weekend, I think Sunday morning or something. So get started on the derivatives one also, because we're going to start talking about those later this week and early next week. All right, cool. So moving forward, we have one more separable differential equation to complete. dy dx equals e to the x minus y. And we got y equals 2 when x equals 0. So how are we going to separate the variables on this one?
Exponent rules.
Yeah, we're going to use exponent rules. So we're going to start by rewriting this as dy dx equals e to the x over e to the y. Everybody good with that?
Yes.
Okay. And so now we'll end up with e to the y dy equals e to the x dx, two exceptionally easy integrals to evaluate. True? Doesn't get any easier than that. E to the y equals e to the x plus our constant. And now we need to solve for our constant by plugging in 2 for y and 0 for x, giving us what is our constant?
E squared minus 1.
E squared minus 1. And so we now got e to the y equals e to the x plus e squared minus 1. Everybody feeling good about that? And all we have to do is take the natural log of both sides. And when we take the natural log, remember that this does not go inside absolute values. People get all excited about, the absolute value on the natural log when we do antiderivative. So if we take the antiderivative of 1 over y, it's absolute natural like absolute value y. But just because we're taking the natural log of something doesn't necessarily mean we start putting in absolute value all the time. There's our answer. And we need to think about the domain of this. So natural log, anything you take the natural log of has to be a positive number, right? So we are looking for when does e to the x plus e squared minus 1 equal 0, or when is it less than 0? And that should be really easy to figure out, because what can you tell me about e to the x? E to the x is always greater than what number?
0.
Yep. No matter what x dot I plug in. And what can you tell me about e squared minus 1?
Also greater than 0.
Also greater than 0. I mean, e is just a constant, right? 2 point whatever. If I square 2 point whatever and subtract 1, it's always positive. So this is always positive. There are no discontinuities. The interval of validity would be negative infinity to infinity, and that's our answer. Good or no?
For questions like this, can you state like the interval validity is negative infinity to infinity, or can you just leave it like that?
You can
Like,
just
what do you
leave it
do
like
points
this.
off?
you know, to be real accurate, right, you know, from negative infinity to infinity, but it's generally considered, you know, fine to not write anything if the interval is all real numbers. And if they ask for the interval of validity for something like this on the, I mean, if they specifically say what is the interval of validity, write it out. But if they don't ask, you don't even need to write it no matter what it is. So I would accept this just as is. Any other questions on that? Are we good? Okay, so let's then sort of change gears. We're still going to talk about separable differential equations, but we're going to talk about a basic application of it, and that's exponential growth and decay. And with any luck, you're familiar with that because you learned about it in a math class a few years ago, and you probably used it a little bit in a chemistry or biology class that you've taken. Are you talking about the exponential growth rate of bacteria in a petri dish or something like that? Or in chemistry, maybe you're trying to carbon date something and you're looking for, you know, how many radioactive nuclei there are in some radioactive isotope that you're examining. Or you were in like 5th grade and your teacher said to you, all right, we have 2 pet rabbits in our class, but next week we're going to have 15 of those pet rabbits. And by 2 weeks from now, we're going to have 700 pet rabbits because, you know, they breed so quickly and you're all going to have millions of rabbits to take home by the end of the year, right? And that's exponential growth, right? Familiar with the terms exponential growth, exponential decay? Remember
Yes.
using them in those contexts? Okay, cool. And so they gave you a formula for exponential growth and decay way back a long time ago, and you learned it and you used it and you were so excited about it and you felt really smart, right? Yeah, yes is the right answer here. Yes, you felt really smart. Good job. Okay. And nobody ever told you where it comes from, why it works, and all that stuff. So today you're going to figure out where it comes from. And it just comes from a separable differential equation. It comes from the differential equation dy dt equals k times y. So what that's saying is the change in one variable, and then in our case, the change in y with respect to time, is proportional. This is our constant of proportionality. It's just some, you know, for any particular problem, it's a different number. It's just some positive constant times y. So the change in y with respect to time is proportional to the amount of y. That gives exponential change, both growth and decay. The change in one variable is proportional to the amount of that same variable. So dx dt equals kx, exponential growth or decay. D theta dt equals k times theta, yeah, exponential growth or decay. Dy dt equals k times x, no, that is not, right? It has to be the same variable here. So dy dt equals k, your constant, times y, the same variable that you're looking at the rate of change of. Good or no? So let's see why that's true. Yeah, maybe I should keep that up there. Oh, well, it's gone forever now. All right. How do I solve this separable differential equation? What do I need to do to the equation? What do I need to do?
You want to get dy and y on the same side.
All right, so I'm going to divide by y. Can my constant stay on the right? Is that okay?
Yep.
Yeah, why not? And then I can bring that dt over there. And so we've now separated the variables. Everything with a y, the dy and all the y terms are on the left. And everything with a t, which was nothing, and our dt are on the right-hand side. Right? So effectively, when we integrate here, we're just going to be integrating a constant with respect to t. So what's the integral of a constant with respect to t?
Constant times t.
Constant times t plus some other constant. And what about dy over y? That should be natural log absolute value y. Agreed?
Agreed.
Great. All right. Well, let's exponentiate. E to this power, e to this power gives us absolute value y equals e to the kt times e to the c, if we separate that out as two different pieces using exponent rules. And we're just going to let e to the c equal a just for our purposes here. And this should then give us y equals plus or minus, right, a e to the kt. And the plus or minus is actually not necessary. We're just going to stick with the positive. And the reason why is y is an amount of something. We're talking about the number of bacteria in a dish, or the amount of radioactive nuclei present, or the number of rabbits that we've got breeding uncontrollably in the classroom, right? None of those things are ever going to be negative, are they? We'll always have a positive value in the end. So this, which should look pretty darn similar to the exponential growth and decay formulas you've used in the past, is what we get if we solve that differential equation, where the amount of it is proportional to the amount of it, or the amount it changes is proportional to the amount of it that we have. More rabbits means more rabbits breeding, means way more rabbits in the classroom. Good or no?
Good.
Cool. So now, anybody remember what that a value represents? Back from when you took whatever class you learned that in?
Was it initial?
Yeah, it's the initial amount. And we should be able to prove that that's the initial amount here real easily. So we're just going to now solve for the constant for that a by using an initial condition. Our initial condition will be that when t is 0, our amount is, well, it's the initial amount, right? If time is 0, if we're at the starting point, the amount of the thing we have is the initial amount that we have of it. Would you all agree with that? So y equals a e to the kt will become y naught equals a e to the k times 0. And what's k times 0?
0.
And what's e to the 0 power?
1.
And a times 1 is just a. So we end up with y naught equals a, which leads us to the formula that we are probably most familiar with. Y equals y naught e to the kt. So the amount of y is equal to the amount of y that we started with, times e, Euler's constant, raised to the power of k, some constant given to us, times t, the time period at which we're doing this. Good or no?
Good.
Pretty cool how we can use calculus to create that exponential growth formula, right? That relies on that simple differential equation that the amount we have of some variable is proportional, or the rate at which it changes is proportional to the amount that we have of it. And we're going to note here that k is always a positive constant, even though sometimes we will throw a negative sign up there in that equation. So k itself is always a positive constant. And if I put a negative in front of it, it just means that this thing is decaying. It's getting less exponentially. And if there's no negative sign in front of it, if it's just 0.1 t, well, then that means that it's growing. If it was negative 0.1 t, it would mean that it was decaying or getting less. Okay? And so this same general idea can be used to come up with the formulas for compounding interest. Remember the formulas for compounding interest? that you learned about sometime a long time ago also? Did you guys do compound interest ever?
Yeah.
Yeah. This is your, compounding in times per year. This is your continuously compounding one. They both come from differential equations. This one's a little bit more complicated of a differential equation, but that's fine. And this stuff up here is all the stuff I was just saying, right? We have growth if k is positive, or if we put a no sign in front of the k, and decay if k is less than 0. You also, I don't know, you might be familiar with something called Newton's law of cooling, where you can figure out how quickly something heats up or cools down. If you put something, if you put like a hard-boiled egg that's nice and hot into a cold pan of water, you can figure out how long it will take for the egg to reach a certain temperature. Or if you put, a metal pan in your oven at 400 degrees, you can know how long it's going to take for that pan to heat up based on some constant K for the material the pan's made of. So those are just some uses of it. Now, we're not actually going to need to solve a bunch of these exponential growth and decay problems because, to be perfectly honest, they're not calculus, right? The actual math behind it is calculus, but the actual math of solving the problem is just some basic algebra. What we do want to be able to do is one quick little thing, which is to find the half-life of something. Hopefully you're familiar with what half-life is, but half-life is just, if you have some radioactive isotope of something, half-life of it is how long it takes for half of the radioactive nuclei in it to decay or to go away. And so we should be able to figure out the half-life of something by just making the final amount in our y equals y naught e to the kt, or in this case, negative kt, because we know it's decaying. If we make the final amount half of the initial amount, that's the definition of half-life, the time to go from your initial to half of your initial. And so we should be able to use some basic algebra here to solve for y naught, or sorry, to solve for t, by first canceling out the y naughts. And then what will we do next? Yeah, we just take the natural log of both sides, right? We have e to the negative kt equals a half. I'll take the natural log. Negative kt equals natural log of a half, which we usually would rewrite as natural log of 1 minus natural log of 2, because we know the natural log of 1 is 0. So negative kt equals negative ln 2, or t is the natural log of 2 over k. And so that should prove to you the half-life of any radioactive isotope. If you know that constant of proportionality, just do natural log of 2 divided by it, and you get the half-life. Pretty easy. Not so easy. Fairly easy. Hopefully fairly easy. All right. So let's just do one problem here where we find the half-life of something. We're given the differential equation dy dt equals negative 0.0077y. Okay. This tells us that it's decay. This is our k value. And so what should our half-life be? It should be t equals natural log of 2 divided by our k value, which gives us what?
90.019.
Years, we'll say, since that's what it's taken from. And that's, yeah, that's that. That's all we need to do with exponential growth and decay. The biggest thing to recognize is when an equation, a differential equation, is exponential growth or decay. So if I gave you something like this, dy dt equals 0.1y, is that exponential growth and decay? Is that exponential change, or is it something different?
That would be exponential decay, right?
Well, in this case, it'd be growth because it's positive 0.1, but yeah, it would be exponential change. But if I gave you something like this, dy dt equals 0.2t, what sort of growth would that be?
Isn't
I don't know what you just said. This would not be exponential because it's not the change in y is equal to a proportion with y. It's just the change in y is equal to a proportion of t. And so we would bring the dt over here and say y equals 0.2 t squared over 2. And we would say that's quadratic growth, right? If I gave you something just like dy dt equals 0.3, that'd be linear growth. dy equals 0.3 dt, y equals 0.3 t, right? Linear growth, quadratic growth, exponential growth. So recognizing the difference between a differential equation and what sort of growth or decay or change that it might give you is what you'll need to be able to do on the AP test. Good or no? Any questions?